Alright, so today we're going to kind of take a bit of a diversion into some group theory. It will all tie back to Lie theory, and particularly the theory of Lie algebras, but you need to do a bit of setup here. So we're going to, first off, we're going to look at we're going to work a bit here with some commutators. So we're going to let G be a group with elements X, Y, and Z, just so we have something to work with here. And we're going to set up some custom notation here. Which I think we're mainly just going to use here. I will give a reminder in case we use it again. First off, we have what looks like an exponent, almost. That doesn't quite make sense because we're working with group elements. And that is just the conjugate of x by y, if that is the correct term. And this is a map from G to G as x to the y. This is an automorphism. And we have the property that x to the y to the x is equal to x to the yx. And this is just, keep in mind, x inverse, y inverse, x, y, x. Or I guess we should call this a bit more generally, we should call this z. Would make a little more sense. And this is just from the fact that inverting a product swaps their order. And the second piece of notation we're going to set up is going to be this weird bracket thing. It looks almost like a Lie bracket, except first off we're not doing Lie algebra, and second we're using curly brackets. And this is the commutator of x and y. So I probably was not using the right term before, but you should have seen this before. Maybe it's the conjugate? Anyways. So we can generate a few identities with these. First off, we have that x times y is just y x to the y. This is easy enough to see because we're just getting rid of that inverse element on the right. And just similarly, y x times the commutator of x and y. Similarly, we can construct x to the y as x times this commutator. We get that the commutator of an element with itself is going to be 1, obviously. And we get that the commutator of if you swap the order of two elements in a commutator, you get the inverse. So these, it almost looks like a Lie bracket in some ways. I wonder if that's kind of what they're going for here. Up next, we have that the commutator of x and the product of y and z. Sorry, 1 second, I gotta get myself set up a little better here. Y and z is equal to the product of the commutator of x and z and x and y to the power z. And a lot of this is mainly just like, you know, algebra, a bunch of like just moving around the symbols. You can work through it, you can get all these results here. And similarly, we have, you can get similar results on the other side. And finally, we have this third setup here, which is meant to mimic, I believe, the Jacobi identity. And this is, of course, going to be equal to 1, which is our group identity. As opposed to normal Jacobi identity, you get 0, which is the additive identity for, you know, an algebra. So I believe what's going on here, this is supposed to be, we'll call this pseudo, this is just stuff I'm writing down for myself here. This isn't official terms, but this is like pseudo alternativity. This here, pseudo, it's not asymmetry, it's anti-commutativity. These two are pseudo linearity, and this here is pseudo Jacobi identity. Jacobity? Whatever, I'm making Jacobiety. I'm making these words up, so I can just call it whatever I want, right? Now, to walk through all these, so I guess we will walk through the proofs of some of these. So, for example, for number 5, we have from before that x times x by yz, this is equal to x to the yz by identity number 2, which is, as we saw before, equal to x to the y to the z. And then this lower element is, as we saw, equal to the product of x and the commutator between x and y. And that whole thing is going to be to the z. And so then we can split this over these terms, because as we saw, this is a morphism. And this gets us x times x, and the commutator of x with z, times the commutator of x with y to the power of z. Then we can just remove this term x on the left to get our desired result. And I guess we'll go through the other side. They have a slightly different proof here. They have this similar structure here. And this is, of course, the product of x and y to the z, which once again we can split over each individual term, which then gives you x, z, using the same properties we saw before. So this is equal to x, y, x, z to the y, and then y inverse here, which cancels out this y, and then y comma z. And once again, if you cancel out this extraneous term on the left, we get the desired result. Finally, there is a proof listed here for number 7. I am debating whether or not I want to go through with it. I have decided not to. It's long, it's a lot of just algebra. Yeah. I hope you can just trust me on this one. So let's look at some applications of this. So we're going to take two subgroups of G. I guess maybe I should write this out and a bit neater. And what we're going to do here is we're going to generalize this commutator kind of in the way you would expect. And this would be the group generated by the set of the individual commutators, because I keep in mind this itself might not be closed as a group, I don't think. So we just take it as a generator inside G and see what we get as a total. And we're out of room here. To the next page. Let A, B, and C be, I believe this is how you write it, in G be normal subgroups. Then we have that this generated commutator of A and B as sets is normal in G. And we also have this relation. I don't know if this is a proper inclusion or not. I guess you could probably have these just all be trivial subgroups, and then it would be, this whole thing would be equal. But kind of what you would expect. Alright. So up next we have filtrations of groups. This is going to circle back around, like I said, to Lie theory. You just gotta bear with me for a bit. So, what is a filtration? A filtration on a group G is a map. We're going to call it, I think they're using W. I'm going to use an omega. I don't know why. It's just kind of how it turned out. From this map's going to go from our group G to the real numbers and positive infinity, this extraneous element, extra element. And of course we're going to have some conditions on this. The first condition is that omega of 1, our identity element, is positive infinity. Our second condition is that omega of x is greater than 0 for all x in G. Our third condition is that omega of x, y inverse is at least the smaller, I'm going to use term minimum, of how it acts on the individual elements. And fourth, it acts on the commutator of two elements from the group is going to be at least the sum of how it acts on each individual element. Alright, so, and we get from number 3 that omega of y inverse is equal to omega of y, and we get this just because if you plug in the identity as x, we get that this minimum is just going to default to the value that omega takes at y. My voice is breaking apart, I'm sorry about that. I wonder if we can take the real numbers to just be like the positive real numbers, since this seems, yeah, this function is constrained to the positive real numbers by condition 2. I'm going to go ahead and write that in for myself. Now, okay. Our next step, for some number lambda in our positive, is the positive better as a suffix? I actually see it as like a, not a suffix, a you know, at the bottom here. I'm gonna write it there for now because that's just what's natural to me. So we're going to find two subsets here of G. The first is derived from lambda directly, and is just the set of elements in G that are at least have a filtration of lambda. And our second condition is we have elements. This is a very similar set, with the only difference being that the filtration of the elements has to be strictly greater than lambda. We don't have this proportion of the elements equal to lambda exactly. And these are not only subsets, but they are subgroups. And that's straightforward to see just from condition 3. We also see that if an element X is inside G lambda, and we have some element Y in G, then the commutator of X by Y, the conjugate, the whatever, is equal to X mod G plus of lambda. Because and we have this because of the fact that omega of the commutator of two elements is greater than or equal to their sum. Omega of X is equal to lambda by definition. And we have equal to or greater than lambda. And Y is just going to be omega Y. And this is going, because this has to be positive, this has to be strictly greater than omega. And this also gives us that this set G lambda is a normal subgroup of G. And since we can construct G lambda positive as the union of smaller G, ordinary G of these groups, we can then say that G lambda positive is also normal inside of G. And we see that the family of groups here that form G lambda is basically getting smaller as lambda gets bigger. As lambda less mu gives us that G lambda contains G mu. And a similar construction for G positive lambda. And this is just because if mu is bigger than lambda, then for omega of x to be bigger than lambda, it has to be bigger than mu, it has to be bigger than lambda. So this is a very obvious inclusion. Another definition here. We're just going to keep building stuff up here. For all alpha at least 0, we're going to define the GR. I don't know what that actually is supposed to stand for. GL alpha of G to be G alpha over G positive alpha. And GR of G to be the sum of all of these possible GRs. And so, like, essentially keep in mind, GR alpha is the set of elements of the filtration of at least alpha, and GR positive alpha is, GR alpha is the set of all elements of the filtration equal to or greater than alpha, and then GR positive of alpha is the set of elements with a filtration strictly greater than alpha. So we have the set of elements with a filtration equal to or greater than alpha, and then we're kind of modding out the greater than. Alright. So we have a few propositions to go along with this. First off, we have that each of these GR alphas is an abelian group. Secondly, we're going to let each x alpha, x bar is going to be the image of some element from G alpha, essentially taking elements in G alpha and them modding out G positive of alpha. The actual proposition is that the image of x to the y mod G alpha positive is equal just to the image of x in G alpha positive. That holds for any y in all of G. Yeah, okay. So they give, we're gonna have a couple more propositions, but I'm gonna try to work through some of the details here myself of these two, because they kind of gloss over everything a bit. So this one, they say, follows from this condition we had that omega of the commutator of x and y is at least x and y, and this should be their sum and not whatever a comma would mean in this context, which I believe is nothing. And so if So saying that GR alpha is abelian is saying that the commutator is always 0, right? Or at least that is an equivalent. And so it's saying that, which would mean this omega on the right is always going to evaluate to infinity? No, that's not right. This might be something I have to work with my own time. I don't want to spend too much of the video just like staring at this, but this is the idea. And element 2 is just based off of, we have here that x to the y equals x mod g plus lambda, and that's literally what number 2 is here, so that we've already covered. I'm just gonna make a little note for myself here. And there are a couple more propositions we have to go through. Proposition 3 here is the map C of alpha and beta from G alpha, the Cartesian product of that, with G beta to their sum. And this is just taking two elements and sending them to their commutator. And the idea here, this induces a bilinear map C bar of alpha and beta from GR alpha of G to and GR beta of G to what you would expect, GR of alpha plus beta of G. And we have a second proposition to go along with it, which is this bilinear map we have generated. We can extend this by linearity, as in two words this time and not bilinearity, to a new map just called C from GR of G by GR of G. Keep in mind this GR of G is the direct sum, is the sum of all GR alpha of G's. And here's where this all starts to wrap back around, is this defines a Lie algebra on GR of G. This is where everything starts to come back around for us. And let's see how much time we have, because it's hard to tell with my current setup. I got 35. So we got a bit. We can work through this proof at least. So we're going to prove these two things here. So first off, we're going to show that we can extend this conjugate map to a full bilinear map on the GR alphas. So, for number 3, we're going to take two elements, call them x and x prime, from G alpha. And similarly, we're going to take two elements, y and y prime, from G beta. And we obviously have that their conjugate term is going to be inside G of alpha plus beta. So we need to show that if we have two elements called mu and v from G alpha positive, then x of x times u with y is equivalent to x conjugated with y mod of G positive alpha plus beta. And we need to show basically the same construction on the other side. This is also xy mod G positive alpha plus beta. So, how can we do this? We have that x, u, y, and then we're taking the, keep in mind, this is the image from this inside gr alpha of g. So this is essentially modding by G positive of alpha plus beta. And this is equal to, of course, xy to the u plus uy, these things as images. This is from a roll we saw earlier, and this gives us xy. And we have very similar constructions on the other side. I'm going to write this as xv, xy to the v, and this once again gets us where we need to be, xy bar. Now, next thing we need to do is look at xx prime by y. Because keep in mind, this is showing the product with an element from G alpha positive. We're now looking at the product of an element from just G alpha itself. And we get the kind of analogous construction here. I guess what I should mention here, I should explain the first two a little more. So going from the second term to the third term in these first two equations, in this first example, we saw before that when we're taking this image by this quotient map, the exponent thing here of u is going to disappear. So x comma y to the u bar is just going to be x comma y bar. And then u comma y is going to be greater than we need, because keep in mind u is from G alpha positive, so it has to be strictly greater. So this has to get quotiented to be the identity. So that term is just going to disappear. And we have and it works exactly the same way with the other case on the other side. Now in this case, once again, we have that taking the quotient disappears our exponent, so we get x comma y bar. And the term on the right is going to stay. And so we get that this product inside commutes with this conjugate and the quotient to give us just a normal sum. And once again, we show that it's linear on the other side with much the same setup here. Bar, this extra term shows up as an exponent and it gets killed by the quotient map. And we're left with a nice little bit of linearity here. So this is bilinear. I guess maybe I should write that, but it's bilinear and it works well across the equivalence classes we are generating with this quotient map. So what we have left to show here is the condition number 4, which was this new quotient map from the gr alpha of g and the gr beta of b to the gr of the sum of alpha and beta of g. We want to extend this to a map on just gr of g by gr of g. Essentially just a binary map on gr of g, and that is going to give us a bracket, and that's going to give us a Lie algebra. So let C be an element in gr alpha of g, and going to let eta be an element of gr beta of g. We're going to choose some elements x in g alpha and y in g beta such that the image of x is c and the image of y is epsilon. So essentially these are just representatives of the equivalence classes that C and eta are meant to show. Then we have that the quotient of the commutator here is from before C bar alpha comma beta of their images, which is just as we defined there, C and eta, which we're going to write definitionally as our bracket. So we can think of C as being just from gr of g in general. Then we have that we can write it as the sum of constituent terms C alpha with each C alpha coming from its corresponding gr alpha of g. Now we need to show we need to start showing like the properties of the Lie bracket. We have its bilinear already from before. So we have that it is going to be alternative if we can show that essentially this is going to, by bilinearity, this is going to split across each of our Xi alphas. So we just need that each Xi alpha cancels out with itself, and that the off-diagonal elements, Xi alpha with Xi beta, are going to cancel each other out by anti-symmetry. So we're going to pick some X alpha from G alpha such that X alpha bar is equal to Xi alpha for all alpha. That's kind of confusing notation, but oh, I guess no, we're just picking a bunch of X alphas, I guess is what's happening. Then we have each of that we can rewrite this term we have here as in terms of these x's and the quotient map. And this is obviously going to give us just 1 and the quotient map of that, which is going to reduce down to just 0. Similarly, for our other condition here, this is going to give us the quotient map of X alpha and X beta, quotient of course, which we can swap their order with an inverse, which is then going to just be, this inverse is going to just turn into a negative here. Now, what's left to show that this is a Lie bracket is the Jacobi identity, which we're going to write we do not writhe. I mean, I do sometimes. We're going to write the Jacobi identity as J, and the 3 terms I'm going to use are Xi, Eta, I don't even remember what this one's called, to be honest with you, and 0. And this function J, you see what it's going to be. It's going to be like the bracket of 1 with the other 2 plus, and then just cycling through all 3 options as you'd expect. And this is of course trilinear by the bilinearity of the Lie bracket. So we can boil this down to just an arbitrary case. And we're going to say let Xi be gr alpha of G, Eta be gr beta of G, and I wish I remember what this one was called, BGR gamma of G. And once again, we're going to pick some representatives here for these terms. I'll write them directly below. X and G alpha y in g beta, and z in g gamma. Now we have that our Jacobi identity of these three is going to be the image of x to the y bracket yz, and as you'd expect, we get every possible permutation. We get all, not every permutation, just the 3 rotations of this. And once again, as always, we take the quotient map, and all of these terms by symmetry are going to boil down as before, keeping in mind that this xy bar is going to be C, yz bar is going to be eta, and zx bar is going to be this thing. So it's been about an hour. Let me check real quick how much longer we have to go. Okay, we're like, we are halfway through this again, so I guess I'm thinking next time we might just, this is about a session length, we're gonna call it here, and the ideas we're kind of started here, we're going to finish off tomorrow, and then we're going to move on to some more normal stuff, I guess you could say, more standard stuff. This is all a bit on the denser side, and it's not going to be important for a while, so this is, you know, like, to be honest, there's a couple things I need to go over again, but yeah.